The next thing we want to look at is how solutions are soluble. Like what happens and what's our limit on solubility? There are relationships between solubility and temperature and solubility and pressure. And then we've got this interesting thing with unsaturated, saturated, and supersaturated solutions. Hopefully this is a review of prep chem because we do go over all this stuff in prep chem. So I'm going to go through it a little bit quickly because this should be a review. All right, let's look at it. All right, so solubility. What is solubility? It is the maximum amount of a solute that can dissolve in 100 grams of solvent at a given temperature. Okay, so everything has its own limit on solubility. So 100 grams of a solvent at a given temperature, the solubility is the maximum amount. Now, once we start making a solution, then we can decide if our solution is unsaturated, saturated, or supersaturated. All right, so what is a saturated solution? A saturated solution is a solution that contains the maximum amount of dissolved solute that will dissolve at a given. All right, so let's say I have a solution. Okay. All right, I'm going to add a crystal. Or crystal. All right, and my crystal sank to the bottom. The original solution was saturated. Okay, so my solution was already saturated and I added another crystal. Saturated means it was at its maximum limit of solubility. So adding another crystal didn't do anything. It just sunk to the bottom because it couldn't take anymore. Now, an unsaturated solution is a solution that contains less solute than can be dissolved at a given temp. Okay, so what that means is we have our solution. We're going to add our crystal. Now our crystal dissolves. Okay, our original solution was unsaturated because if I had less solute that can be dissolved at a given temperature, that means if I added more, at least as long as I didn't go over the solubility, it could dissolve. Like let's say sodium chloride, it has a solubility of 33 grams for 100 grams of water at 100 degrees Celsius. So let's say I had a solution that only had 15 grams in it. If I added another gram, it would just dissolve because that's still under the solubility. Now, the really interesting case is supersaturation. So a supersaturated solution is a solution that contains more dissolved solute than will ordinarily dissolve at a given temp. Now, supersaturated solutions are really interesting. They're super unstable, all right? Doesn't take much to perturb them. What happens is, for most solid solutes, when we raise the temperature of our solvent and thus the temperature of our solution, we can get more to dissolve, all right? We raise the temperature, we raise the solubility. Most of the time what happens is as we cool that back down, the excess solute comes back out of solution because at lower temperatures, there's lower solubility. However, there's some substances that if we're really careful with it, as we cool it down, that excess amount will stay in solution. And it's not a very stable solution. Okay, so what happens here? Let's start off with our stack. Let's start off by, okay, we've got our solution. We're going to add our crystal. And then what's going to happen is excess crashes out. So a whole bunch of that excess solute now comes out of solution. So we can't keep that excess in there. As soon as that seed crystal hits, the rest of the solution sees that seed crystal and it starts crystallizing out from where that seed crystal is. It crystals because it goes, wait a second, at this temperature, we're not supposed to have this much in solution. Whoops, we better all crash back out again. So our original solution was supersaturated. Now what happens is it keeps crashing back out until it's back to its normal solubility. So the resulting solution is now saturated, but the original solution was supersaturated. All right, now what happens is everything is dynamic. Nothing is just static. So even that situation where the seed crystal fell to the bottom in a saturated solution, things are bouncing around. Okay, my water molecules are bouncing around, or whatever my solvent is, those are bouncing around. They hit the solid. Okay, as they hit the solid, they interact, but some of those ions that are already in solution, or some of those, solvated particles, like say we have sucrose. It's not ionic, but it is soluble. So let's say one of those particles hits. Well, now another particle can dissolve, and another particle hits, and another particle can dissolve. And we reach equilibrium when the rate of dissolving is equal to the rate of redeposition. All right, and so it's very dynamic. It goes back and forth. So we reach that equilibrium when our rate of dissolution equals the rate of deposition. That's our dynamic equilibrium. Right? And if we have something that's saturated, we've got that excess crystal sitting in there. And so again, ions are hitting it, more ions are dissolving. Ions are hitting it, more ions are dissolving. And so we get this equilibrium with our solute that is undissolved and our solute that's dissolved. It doesn't mean that the amounts are equal. It means that the rate is equal. Okay? And then here's a better picture of that supersaturation. The seed crystal went in and a whole bunch of stuff came out of solution. So it's a little bit better than my drawing, but hopefully my drawing helped. Okay? Now, when I look at solubility and temperature, all right, so when I look at gases, the solubility decreases as the temperature increases. But when I look at liquids and solids, generally speaking, okay, solubility generally increases as temperature increases. And this makes sense with our gases because, well, if there's a limit on solubility, if we raise the temperature, we get closer to the point at which our solvent is going to vaporize, thus adding more gas, right? But if we're talking about a solid or a liquid, okay, as we increase the temperature, stuff's moving around more, we're able to get more to dissolve. Okay, so here, when we look at our gases, as our temperature increases, you can see that they go down. So solubility goes down as temperature goes up for our gases. Okay, so gases, solubility down as temp up. Okay, but for our solids and liquids, okay, generally, solubility goes up as temp goes up. And I say generally because if you see there, I've got that cesium sulfate, that one went down. But for the most part, temp goes up, solubility goes up. Now, they don't all go up equally. If you look at this, we've got a whole bunch of different slopes, and some of them aren't even completely linear. There are, some curve. So every single solute has its own limit of solubility and its own relationship between solubility and temperature. Some stuff like sodium chloride is already super, super, super soluble. So as we raise the temperature, the solubility doesn't go up a whole lot, but it does go up a little bit. Okay. Now, when we look at pressure, all right, so for liquids and solids, pressure has very little effect on our solubility. But for gases, pressure is incredibly important. All right, so we need pressure to go up for solubility to go up for gases. Okay, so if we increase the pressure, we increase the solubility because we're squishing more down. Okay, and so here at my first pressure, I've got all the space above my liquid. I don't have as many particles in my liquid. But if I increase the pressure, now I don't have as much space for all those gas particles to bounce around. And now I've squished more in there. And so my solubility has gone up. All right. And so for gases, again, the solubility goes up when pressure goes up. Okay. All right. So we have this Henry's law. So Henry's law shows that the solubility of a gas is directly proportional to two components. It's Henry's law constant and the partial pressure of the gas above the solution. All right, so as gas, the solubility of a gas. Case of H is the Henry's law constant. And this is unique for every gas. Okay, and then the P gas is the partial pressure about the solution. Okay? All right, so it's directly proportional to that. Okay, so we have the partial pressure of carbon dioxide in a bottle of coal is 4 atmospheres at room temperature. So what's our solubility? We've got a Henry's law constant, so let's figure this out. Okay, so we get our S of our gas is equal to our Henry's law constant times that partial pressure. All right, so our solubility, we've got 3.3 times 10 to the negative 2 moles per liter atmosphere. We have 4 atmospheres, and so we get 0.132 moles per liter, or 0.13, yeah, because we have 2 sig figs molar. So the solubility of our carbon dioxide is 0.13 molar. All right, now I've got some nitrogen. Okay, the solubility at room temperature in 1 atmosphere is the 6.8 times 10 to the negative 4th molar. Now, what happens if we change the partial pressure to 0.78 atmospheres? What does our solubility change to? Well, if you notice, we don't have the Henry's law constant here, so we're going to have to do 2 parts to this problem. Okay, part 1, we're going to solve for Henry's law. Okay, so we were told that the solubility of our gas at 1 atmosphere was 6.8 times 10 to the negative 4th moles per liter. The math on this is super easy because we just have 1 atmosphere. So anything divided by 1 is itself. So our Henry's law constant is 6.8 times 10 to the negative 4th moles per liter atmospheres. And now we can solve at lower pressure, or whatever our new pressure is. Maybe it was higher pressure, but this one's going to be lower pressure. Okay, so our S is our new Henry's law constant, 6.8 times 10 to the negative 4th moles liter atmosphere, 0.78 atmospheres. Okay, so we've decreased the pressure. So what do you think is going to happen to the solubility? Let's see here. We're going to get 5.3 times 10 to the negative 4th molar. Did our solubility go up or did it go down? It went down, which makes sense because we lowered the pressure. All right, so that looks at our solubility.